This technique involves the works of three people. The surnames are mentioned in accordingly: Rivers, Shamir, Edelman. Basically, as we remember with asymmetric encryption, what it means is that data is encrypted using one key and decrypted using another key. And basically, these are the encryption side of key is known as the public key, and the decryption side of key is known as the private key. And that's usually the case. But if you're using it for authentication, it's reversed: for encryption using private key, for decryption using public key. But anyway, both keys are matched pairs. So what that means is that if you're encrypting using public key for A, it will be only decrypted using private key for A. Similarly, if you're using private key for encryption of private key of B for encryption, it can be decrypted only using the public key of B using decryption. So matched key pairs. So they have to be matched key pairs, and there are two different keys, and this is asymmetric encryption. Now, basically, RSA involves the following algorithm, and in which there's a lot of math involved. So we're going to be going through this one by one. First of all, the first step towards the RSA algorithm is that we select two very large prime numbers. That could be P and Q. And we multiply these P and Q together, and we get their product N. Okay, so first step is this: two very large prime numbers. We multiply it and we get N. Okay. Second step is we take P minus 1, Q minus 1, and multiply that together. We have another product. Okay. Third step, we need another prime number, which is E. And we have to select E in such a way that it is less than P minus Q, P minus 1, and Q minus 1. Basically, it's less than the product of this. It has to be less than the product of this. Secondly, and it should not be a factor of this as well. Once I go through the example, it's going to be a lot more clearer. So selection of E involves these rules. Usually 65,537 is used because it satisfies most numbers, the rule for the most numbers. So basically E is usually this value, but we won't be going for such big numbers as an example because it's going to be easier to solve with smaller examples. Okay, now this E that we just selected based on this rule, that will become my encryption key. Okay, so E for encryption key. Now we guess another number. Now we have to calculate another number. That is known as D. Now D is such a number that it satisfies the condition that the product of D multiplied by E when divided by P multiplied by E, sorry, P minus 1 into Q minus 1, it should give a remainder of 1. So basically what that means is that D, product of D multiplied by E, and it's divided by this, the remainder should be 1. And if this condition is met, the remainder of 1, D will become my decryption key. So I need a number, D, which satisfies this condition. If that condition is met, then D will be considered as my decryption key. So now that I have the keys, I'll be using an equation to perform the encryption. So basically I need the encryption algorithm now. So for encryption, we will use this technique. CT is used to represent my ciphertext or encrypted text, and PT is used to present my plain text. So basically, how do I get my ciphertext? Plain text, power, exponents, the encryption key, and take the mod of n. Using the mod n of this, the result will be my ciphertext. So this is my formula or algorithm or method to find a ciphertext from my plain text. And remember that we calculated n in the first step, and E is my encryption key. Okay. Likewise, when I have my ciphertext and I want to extract my plain text, this is the technique I will be following. My ciphertext, exponent, decryption key, take the mod n, and the resulting value will be my plain text. Okay. Now let's consider this equation right here, these two equations, and let's try to imply the RSA using a numerical example. Now, obviously, I'll be choosing very small numbers because this calculation will be easier to understand with small numbers. But using small numbers does not mean that in reality, RSA is implemented in small numbers. No, RSA is implemented with very large numbers. Just for example, the P and Q that we're selecting on right now, they can be more than 10 digits. So they have to be very large numbers. The larger the number, the more secure the method. But for our understanding, we'll be using small numbers. So let's just say the two numbers, the two large numbers P and Q, large prime numbers P and Q that would be to be chosen are 7 and 17 respectively. So P is 7, Q is 17. For the sake of understanding easy calculation, small prime numbers are used. In reality, these numbers are very large, even more than 10 digits. Second point to note here is that since I'm encrypting plain text to ciphertext, I'll need numerical values against the plain text values. So the scheme that's discussed here is that for letter A, I'm going to call it number 1, B is 2, C is 3, D is 4, E is 5, so on and so forth. Okay, so if I have, and that should also go for symbols and spaces and so on and so forth. So any text that I want to convert into my encrypt ciphertext, I have individual binary values for each and every letter or character in my plain text. Agreed?
Yeah, each character is given a value essentially.
A binary value, okay? And this is the value we've chosen, it could be different, but right now for the example, we've just said that, okay, let's just say that A is 1, B is 2, and so on and so forth, okay? Now, let's calculate the decryption key first, okay? So P is 7, Q is 17. The first thing I need is N. So as you can see here, 7 into 17 is 119. So that's N right there. Now, the next step is we need E. Now, E has to be less than the product of P minus Q, P minus 1, and Q minus 1. It has to be less than the product of that. Secondly, it has to be a number which is not a factor of the product of this. So basically, let's first find out what P minus 1 into Q minus 1 really is. So technically, P minus 1 will become 6, Q minus 1 becomes 16. So multiply 6 into 16, I will get 96. Now, E should be a number which is lesser than 96, and also a number which is not a factor of 96. Agreed? So considering these two rules, that E has to be lesser than the product of P minus 1 into Q minus 1, and it should not be a factor of 96, we've chosen 5. 5, it could be other numbers as well, but 5 seems like a good example. The 5 is a small number, it's smaller than 96, and secondly, 5 can never be a factor of 96. There's no aspect of 5 or anything here in this 96. So 5 satisfies both conditions. So in this case, since 5 satisfies both conditions and 5 should be equal to E, we're going to say that 5 is now my encryption key. Okay. Secondly, we have to calculate the decryption key, right? Now, the decryption key states that if I take 5 as my encryption key and I multiply D with it, right? My D should be such a case that if I multiply D with E and take the mod using this value, my answer should be 1. If with the value of D, such situation is met, that if I multiply D by E and take the modulus from this value, If the answer is 1, then D will be my encryption key. So in that case, if I have chosen E as 5, let's see what D should be, right? So let's just say we want to send the letter F. Oh, right. So D should be 77. Now, why should be D should be 77? Because 77 satisfies this condition. When I multiply 77 by E and take the mod from Q minus 1 and into P minus 1, my answer is 1. So trust me, this value is true. It's perfectly fine. So 77 satisfies this condition. It could be other numbers as well, but right now we've chosen 77, right? So 77 is chosen because D as 77 satisfies this condition that when I multiply D by E, take the modulus of that with this, the answer should be 1. So in that case, D should be a perfect number. So in this case, 77 is the value of D, okay? Now, I have D, the decryption key. I have E, the encryption key. I have the methods of encryption and decryption. Now let's just say, let's work out this example, right? So let's just say we want to send the letter in F in encrypted form. Just one letter is considered for this simple example. It could be more, of course, it could be paragraphs, pages, whatever. But for the example of, and for this example alone, we're just going to consider only one letter is being sent. Now this one F has to be encrypted. As the scheme mentioned before, A is 1, B is 2, C is 3, D is 4, E is 5. According to that, F should be 6, which it is. Therefore, when I'm calculating the ciphertext using this technique right here, using this technique, I'll be using the value F as my plain text, as value 6 for F as my plain text. So as you can see here, my plain text is 6. E has already been calculated as 5. I will take the mod of this value with Q minus 1 into P minus 1, which is 109, which is hello? Okay. So to create encrypted text, we have the plain text, which is 6, because we're transferring F. We take the exponent using E. E is 5. And we take a mod from N. N, as we calculated before, is 119. Q is 17 and P is 7. So N is 7 into 17, P and Q. So that's 119. So PT, plain text, exponent the encryption key, modulus 119. So whatever the answer is, that will be my ciphertext. So in this case, if I say convert my F into 6, take the power 5, and perform a modulus from 119, my resulting answer will be 41. So in this case, my ciphertext is 41. So when I encrypt my F, my resulting value will become 41. So this is how encryption takes place. Agreed? So F, when encrypted, becomes 41, right? Now let's see what's happening on the flip side, on the reverse side, when your data is being received and it has to be now decrypted, okay? On the receiving end, the ciphertext will be encrypted using a different key. As you remembered before, we have chosen D as 77 as our decryption key because it satisfies this condition. It satisfies this condition, right? Okay.
Do you send when the actual transfer is taking place?
Yeah.
Do you send the decryption and also the value N
No, we don't
along
send.
with
We
ciphertext?
just send the ciphertext.
Then how does the second party know what to use?
Because
Oh, because it has the rules. Okay,
key pairs, and secondly, the rules are there, right? Okay, now we have D as my decryption key, which is valued at 77 because it satisfies this condition. My ciphertext is 41, like this. Now I want to proceed towards calculating my plain text, right? So 41 exponent 77, because D is 77, ciphertext is 41, and mod it from using 9, N 119. So when I do that, my answer should be 6, which is actually my original text, F, right? So this way you can see when the ciphertext is input and applied, the formula and the values are applied, I am ending up with my original values, which is 6 in this case for F. Now, this calculation may seem pretty huge, and it is, but this really is the answer, 6. This really is the answer. This is an online calculator that I use, and it's basically calculating very large values. This is the link for it. As you can see here, if I use base 41 and exponent 77 and perform a modulus 119, the answer of this expression is 6 and 6. So safe to say, I am back with my original text, my plain text, that is 6. So this is a simple example of how the RSA algorithm can be used with 2 different keys. In this case, I'm using E as my encryption key, D as my decryption key. Agreed?
Agreed, sir.
Okay. So this is how the RSA algorithm is being used. It's actually a very simple algorithm. You just need to be, familiar with the proper calculations and be able to calculate the numbers that are suitable for the conditions for both encryption key and the decryption key. Okay. Okay. Now in the subsequent lecture, we'll be discussing the symmetric encryption technique, which is known as your SDES method.
So this was the RSA method.